All right, let's talk about one of the coolest tools in machine learning, the support vector machine. Now, I know what you might be thinking. Complex math, right? Nope. We're going to break it all down with a simple story. It's got a town, two kinds of fruit, and, well, a whole lot of chaos.
So here's the game plan. First, we'll visit the chaotic town of Dadanagar. Then we'll try to draw the perfect line to solve their problem. Things get tricky with a surprise hybrid fruit. After that, we'll learn how to tune our solution. And finally, we'll connect all of this back to why it actually matters. Let's get into it.
All right, first up, the chaos in Dadanagar. We're going to see how a simple marketplace problem can actually explain a really complex algorithm.
So picture this. You're in this busy town called Dadanagar. The marketplace is just a mess. You've got vendors, Manju with her mangoes and Omi with his oranges, and they are tearing their hair out. Why? Because the mangoes look like oranges and the oranges look like mangoes. Some mangoes are tiny and round, some oranges are kind of long and oval. You can't tell them apart just by looking, and everyone is arguing. It's total chaos.
So to fix this fruity mess, the town brings in the big guns, Professor Valmiki Verma. And he has this brilliant idea. He says, look, this isn't a fruit problem, it's a data problem. So what does he do? He takes every single piece of fruit and plots it on a graph. On one axis, you've got its size, and on the other, how intense its color is. And just like that, all that chaos starts to make a little bit of sense.
Okay, part 2, drawing the perfect line. Now that the professor has all the fruit plotted out, the real question is, how do you find the best boundary to split them up? And this right here is the key question. I mean, you could draw a line pretty much anywhere, right? A little to the left, a little to the right. There are tons of options. But in machine learning, good enough doesn't cut it. We need the best line, the one that's most confident, the one that's going to work best for future fruits we haven't even seen yet. So that dividing line, it's got a fancy name, of course. It's called a hyperplane. Now, don't let the name scare you. In our 2D graph with size and color, it's literally just a line. If we added another feature, like, say, texture, we'd be in 3D, and the hyperplane would be a flat plane slicing through the space. It's just the name for the boundary, no matter how complex things get. Okay, so how do we find the best hyperplane? Well, this is where the magic happens. Professor Verma introduces this idea called the margin. I want you to picture it like a street, okay? A big, wide street that runs right between the mangoes and the oranges. The hyperplane is just the yellow line painted down the middle of that street. And the whole goal of a support vector machine, the entire point, is to make that street as wide as it can possibly be. We want the biggest possible gap, the biggest buffer zone between our two groups of fruit. Now, take a look at the fruits that are right up against the edge of our street, the ones basically sitting on the curb. These are special. These are the support vectors. And honestly, they are the most critical pieces of data we have. Why? Because they are the only ones that decide where the street goes. If you move any other fruit, nothing changes. But if you move one of these support vectors, even a little bit, the whole street and the line down the middle has to move with it. They literally support the position of the boundary. That's where they get their name. All right, next section, the hybrid fruit twist. Just when things are looking good, a curveball gets thrown into the mix. What happens when our data isn't so simple? So this hybrid fruit lands smack in the middle of our nice, neat groups. A straight line is useless now. But Professor Verma, he's got one more ace up his sleeve. It's called the kernel trick, and it is so clever. Basically, he says, what if we look at this from a different dimension? He adds a new feature that essentially lifts that tricky hybrid fruit up off the flat page. Now, when you look at it in 3D, you can just slide a simple flat plane right underneath it, separating it from everything else. And the coolest part? When you project that flat plane back down onto our original 2D graph, it looks like a perfect curve that wraps right around the hybrid. It's like magic. Moving on to tuning the gatekeeper. We're going to get into the nitty-gritty of the cost and gamma parameters. Because having a curvy line is great, but we need to control exactly how it curves, right? Yeah, just think of the SVM as a super strict gatekeeper. Its one and only job is to stand at the border and make sure mangoes stay on the mango side and oranges stay on the orange side. The parameters we're about to talk about, cost and gamma, are basically the rulebook we hand to this gatekeeper. They tell it exactly how to do its job. First up is cost, which we just call C. Think of this as the gatekeeper's personality. A low-cost C means you've got a pretty chill gatekeeper. It's like, if one or two fruits are on the wrong side, it's not the end of the world. Let's just keep the main street nice and wide and simple.
This is great for generalization, but a high-cost C? Oh, that's a super strict gatekeeper. It's going to try to classify every single fruit perfectly. The penalty for getting one wrong is huge. This can create a really narrow, complicated boundary that's perfectly tailored to the fruit it's already seen, but it might totally mess up when a new, unexpected fruit comes along.
Okay, then there's gamma. This one's a little different. Gamma controls how far the influence of a single fruit reaches. If you have a low gamma, every fruit is like a big planet with a lot of gravity. Its influence pulls on the boundary from far away, which creates a really smooth, general-looking curve. But if you have a high gamma, each fruit is more like a tiny little pebble. It only has influence on the boundary that's right next to it. This can lead to a super complex, kind of wiggly line that tries to wrap itself around every single data point. So, when you put it all together, you get this amazing level of control. Cost, or C, that's the gatekeeper's strictness. The kernel is what kind of fence it can build, straight or curvy. And gamma is the influence radius. Is that fence going to be a big, smooth curve, or is it going to be super detailed and wiggly? Getting the balance of these just right is the key to making an SVM work perfectly.
All right, last section, why this matters. So a story about mangoes and oranges is fun and all, but why do you care? Well, it turns out this exact same logic is running behind the scenes in so much of the tech you use every day.
The reason SVMs are so powerful is because they're great at a few specific things. First, they're awesome in what we call high dimensions, when you have tons of features, not just two like size and color. They can also work surprisingly well even if you don't have a massive amount of data to train them on. And they are just so versatile. We're talking about everything from image recognition and financial analysis to classifying text.
So let's just quickly recap the big takeaways here. 1. SVMs are all about finding that optimal boundary by making the street, or margin, as wide as possible. 2. The support vectors are the crucial points that actually define where that street goes. 3. The kernel trick is our secret weapon for handling complex, messy data. And 4. Those knobs we can turn, cost and gamma, let us fine-tune everything to strike that perfect balance between being accurate now and being accurate in the future.
And that really brings us to the big idea here. This whole system, this whole way of thinking that sorted out the fruit market in Datanagar, it's not just a story. It's working silently all around you. So think about it. From filtering the spam out of your email to helping doctors diagnose diseases, where are these invisible gatekeepers making decisions for you every single day?